Today we'll discuss ISI's BSTET 2011 UGB paper, and the first question is, let x1, x2 and xn be positive real numbers such that x1 plus x2 up to xn is equal to 1. Then we need to show that this summation I varies from 1 to n xi upon 2 minus xi, it is greater than or equal to n upon 2n minus 1. Now if we consider this expression on the left hand side, we can write this as this summation I varies from 1 to n xi upon 2 minus xi. Now we'll add 2 and subtract 2. We can write this as this summation I varies from 1 to n minus 1 plus 2 upon 2 minus xi, which is minus n plus 2 into this summation I varies from 1 to n 1 upon 2 minus xi. Now we know that sum of all xi's, it is equal to 1. That is, each of xi is less than 1, which simply means that 2 minus xi is greater than 0. So this series, it is sum of reciprocals of positive numbers. Now using AM and HM relationship for positive numbers, we can write arithmetic mean of 2 minus xi, where I varies from 1 to n divided by n, it is greater than or equal to n upon summation 1 upon 2 minus xi. Now this summation 2 minus xi can be expressed as 2n minus summation xi whole divided by n, and will be greater than or equal to n upon this summation 1 upon 2 minus xi. Now summation xi is 1. So in the numerator, we'll have 2n minus 1. So from here we can say this summation 1 upon 2 minus xi, it is always greater than or equal to n square upon 2n minus 1. Now we'll come back to our original expression. So from here we can say this expression is always greater than or equal to minus n plus 2 into, now for this summation we can replace it with n square upon 2n minus 1. So we can write this summation I varies from 1 to n xi upon 2 minus xi is greater than or equal to, now we'll take 2n minus 1 common, and then it will be minus 2n square plus n plus 2n square. Here 2n square will cancel. So from here we can say this summation I varies from 1 to n xi upon 2 minus xi is greater than or equal to n upon 2n minus 1, which is what we need to prove in this question. Now the second question is, consider three positive real numbers a, b and c. Show that there cannot exist two distinct positive integers m and n such that both a to the power m plus b to the power m equals c to the power m, and a to the power n plus b to the power n equals c to the power n whole. Now clearly it is given that m and n are two distinct integers. That means m is unequal to n. Now without loss of generality, we can assume that let m be less than n. Now we are given that a to the power m plus b to the power m, it is equal to c to the power m. And since a, b, c are positive real numbers and m is also a positive integer, that means a is less than c and b is also less than c. Now since n is greater than m, if we take the power n minus m, we can say a to the power n minus m will be less than c to the power n minus m, and b to the power n minus m will be less than c to the power n minus m. Now we'll begin with c to the power n. We can write this c to the power n as c to the power n minus m into c to the power m, and c to the power m is a to the power m plus b to the power m. So we can write c to the power n minus m into a to the power m plus b to the power m, which we can also write as c to the power n minus m into a to the power m plus c to the power n minus m into b to the power m. Now c to the power n minus m, it is greater than a to the power n minus m. And the same way, c to the power n minus m, it is greater than b to the power n minus m. So we can say that this is greater than a to the power n minus m into a to the power m plus b to the power n minus m into b to the power m. Now here it will be equal to a to the power n plus b to the power n. So from here we get this condition that c to the power n will be greater than a to the power n plus b to the power n. That means a to the power n plus b to the power n, it is not equal to c to the power n. That means these two conditions, they cannot hold simultaneously. Now the third question is, suppose a function f satisfies f of fx equals x for all x belongs to R. Now this first part is show that f is 1:1. Now what we'll do is we'll let fx equals fy. Now if fx equals fy, then f of fx equals f of fy. Now if we take one more fx, we can write f of fx will be equal to f of fy. Now it is given that f of fx is simply x. So from here we can say this x is equal to y. So when we assume fx equals fy, the only condition that we get is x equals y. That means this function f is a 1-1 function. So this is your part A. Now part B is we have to prove that f cannot be strictly decreasing. So for B, what we'll do is we'll let f be strictly decreasing function. Now if f is decreasing, let us assume let x to be greater than y, and if we take fx, then since f is a decreasing function, fx will be less than fy. Now if we take this f one more time, we can write f of fx will be greater than f of fy, and again if we take one more f, again the inequality sign changes. So f of fx will be less than f of fy. Now this is x and this is y. So from here we get this condition that x is less than y, which is a contradiction. That means this f, it cannot be strictly decreasing function. Now we'll come to its third part. Now we are given that f is strictly increasing. Now what we'll do is we'll let fx is unequal to x. That means fx is either greater than x or less than x. So we consider this first case when fx naught, it is greater than x naught. Now we consider f of fx naught. Now for this function fx naught is greater than x naught. That means it is greater than f of fx naught. Now for this function, this is x naught, so it will be greater than fx naught, and here fx naught, it is greater than x naught. Now this f of fx naught is nothing but x naught. So from here we get this condition that x naught, it is greater than x naught, which is not possible. If we consider the second case, when fx naught is less than x naught, again we can say f of fx naught will be less than f of fx naught, which is less than fx naught, which is less than x naught. So again we get this condition that x naught is less than x naught, which again is impossible, which simply means that our supposition is wrong. That means in this case fx must be equal to x, and that's your part C. Now question number 4 is, let f be a twice differentiable function in the open interval -1 to 1 such that f0 is 1. Suppose f also satisfies fx greater than equal to 0, f dash x less than equal to 0, and f double dash x is less than equal to fx for all x greater than 0, then show that f dash 0 is greater than equal to minus root 2. Now it is given that this function f, it is a twice differentiable function, so we can use Taylor's polynomial theorem. We can write fh will be equal to f0 plus f dash 0h plus f double dash theta h square upon 2, where theta lies between 0 to h. Now since f double dash x, it is less than equal to fx, we can write f double dash theta will be less than or equal to f theta. Now since f dash x, it is less than equal to 0, it simply means fx is a decreasing function, and if fx is decreasing, then f0 will be greater than f theta. So f theta will be less than or equal to f0. fh, it will be less than or equal to f0 plus f dash 0h plus f0 h square by 2. Now f0 is 1, so we can write fh, it is less than or equal to 1 plus f dash 0h plus h square upon 2. Now we know that f double dash x is less than or equal to fx, so we can say this fh will be greater than or equal to f double dash h. Now we'll integrate both sides from 0 to x. So we can write f dash x minus f dash 0 will be less than equal to x plus f dash 0 x square upon 2 plus x cube upon 6. Now we'll integrate this once again from 0 to x. Here will be fx minus f0 minus f dash 0x, and it will be less than or equal to x square by 2 plus f dash 0 x cube by 6 plus x to the power 4 by 24. Now we'll take f dash 0 together. So we can write f dash 0 x plus x cube upon 6, it is greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 plus fx minus f0. Now f0 is 1 and fx is always greater than or equal to 0. So from here we can say f dash 0 into x plus x cube upon 6 will be greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 minus 1. And from this we can write f dash 0 will be greater than or equal to minus x square by 2 minus x to the power 4 upon 24 minus 1 upon x plus x cube by 6. That will be true for any x which lies in the interval 0 to 1. Now this function on the right, it is an increasing function. So this f dash 0 will always be greater than or equal to the value when the value of x is 1. So if you put x as 1, we'll get this as minus 1 by 2 minus 1 by 24 minus 1 upon 1 plus 1 by 6. So it will be minus 37 upon 28, which is nearly minus 1.32. So from here we can say this f test 0 will be greater than or equal to minus root 2, and that is the answer to this question. Now question number 5 is ABCD is a trapezium such that AB is parallel to CD and AB upon DC is alpha, which is greater than 1. And suppose P and Q are points on AC and BD such that AP upon AC equals BQ upon BD equals alpha minus 1 upon alpha plus 1. We need to show that PQCD is a parallelogram. So we consider this ABCD. Now suppose this is A, B, C and D. Now suppose position vector of D is O. So we choose this D as origin. This is C. This is A. And let this be B. Now we are given that vector AB is alpha times DC. Now AB is B minus A and alpha. DC is simply C. So we can write this B as A plus alpha C. So this position vector of point B will be A plus alpha C. Now it says that we have a point P on AC such that AP upon AC is alpha minus 1 upon alpha plus 1. From here we can say that AP upon AC minus AP will be equal to alpha minus 1 upon 2. That is AP upon PC is alpha minus 1 upon 2. So we have A, which is A, and then we have this C, and then we have this point P, which divides AC in the ratio alpha minus 1 is to 2. From here we can write position vector of this point P. It will be alpha minus 1C plus 2A upon alpha plus 1. Now we are also given that there is a point Q on BD such that BQ upon BD is alpha minus 1 upon alpha plus 1. And in the same way as we did previously, we can write BQ upon QD is alpha minus 1 upon 2. So we have these points B and D, which are A plus alpha C and 0. Then this Q, it divides them in the ratio alpha minus 1 is to 2. So position vector of Q, it will be 2A plus 2 alpha C upon alpha plus 1. Now we'll find this vector PQ. Now vector PQ will be position vector of Q minus position vector of P. It will be 2A plus 2 alpha C minus alpha C plus C minus 2A upon alpha plus 1. Now 2A and 2A will cancel. So we'll get this as alpha plus 1C upon alpha plus 1. That is PQ, it is equal to DC. So these two vectors PQ and DC, they are parallel and equal. And if they are parallel and equal, that means this PQCD is a parallelogram. And this is what we need to prove in this question. Now question number 6 is, let alpha be a complex number such that both alpha and alpha plus 1 have modulus 1. And if for a positive integer n, 1 plus alpha is an nth root of unity, then show that alpha is also an nth root of unity and n is a multiple of 6. Now we are given that 1 plus alpha is an nth root of unity. So we can write 1 plus alpha as e to the power iota 2 pi k by n. Now from here we can write alpha as minus 1 plus cos 2 pi k by n plus iota sine 2k pi by n. Now it is given that mod of alpha is 1. So if we take mod alpha, it will be under root of minus 1 plus cos 2 pi k by n whole square plus sine square 2k pi by n, and it will be equal to 1. Now we square it, we can write 1 plus, now cos square theta plus sine square theta is also 1, and then it will be 2 cos 2k pi by n, and it will be equal to 1. This 1 and 1 will cancel. So from here we can write cos 2k pi by n, it will be equal to 1 by 2. Now 1 by 2 is cos pi by 3. Now we compare, we can write 2k pi by n will be equal to pi by 3. Now this pi and pi will cancel. So we can write this n as some 6k. That is, this n, it is a multiple of 6, which is one part of the question. Now we also have to prove that this alpha is also an nth root of unity. Now cos 2k pi by n is 1 by 2. So if we put 1 by 2 here, we'll get this as minus 1 by 2. So this alpha will be minus cos 2k pi by n plus iota sine 2k pi by n, which we can also write as minus e to the power minus iota 2k pi by n. Now if we take nth power of alpha, we can write alpha to the power n will be minus 1 to the power n, and then e to the power minus iota 2k pi. Now since n is a multiple of 6, minus 1 to the power n will be simply 1. So this alpha to the power n will be e to the power minus iota 2k pi, which is cos 2k pi plus iota sine 2k pi, which is 1. So that means this alpha, it is also root of this equation xn equals 1. That is, this alpha is also an nth root of unity. Now question number 7 is, show that there cannot exist 3 prime numbers each greater than 3 which are in AP with a common difference less than 5. Now suppose these 3 numbers are a plus dn, a plus 2d, where a is greater than 3 and d is less than 5. Now since all these 3 numbers, they are prime numbers greater than 3, they are odd numbers. And if they are odd numbers, that means their common difference, it must be an even number. So this d, it is an even number. When d is less than 5, we have 2 cases. Either the value of d is 2 or the value of d is 4. Now if we take d as 2, then the series is a plus 2 and a plus 4. Now we consider these 5 numbers a plus 1, a plus 2, a plus 3 and a plus 4. At least one of them, it is divisible by 3. Now since a plus 2 and a plus 4, they are prime numbers, they are not divisible by 3. That means either a plus 1 is divisible by 3 or a plus 3 is divisible by 3. So if a plus 1 is divisible by 3, we can write a plus 1 as 3k. Now if we add 3, we can write a plus 4 equals 3k plus 1. That means this a plus 4, it must also be divisible by 3. But a plus 4, it is a prime number. That means there is a contradiction here. So a plus 1, it cannot be a multiple of 3. Now we consider a plus 3 to be multiple of 3. Then we can write this a as 3 into k minus 1. In that case, this a will be a multiple of 3, which again is not possible since a is a prime number. That means the value of d cannot be 2. Now we'll come to the second case when the value of d is 4. Now if the value of d is 4, then the series is a plus 4 and a plus 8. Now we consider numbers a plus 1, a plus 2, a plus 3, a plus 4, a plus 5, a plus 6, a plus 7 and a plus 8. At least one of them will be divisible by 9. Now it cannot be this a, it cannot be a plus 4 and it cannot be a plus 8 since they are prime numbers. Now we consider this a plus 1 to be multiple of 9. We can write a plus 1 equals 9k. Now if we add 3 to it, we can write a plus 4 equals 9k plus 3. Now 9k plus 3 is divisible by 3. That means this a plus 4 will be divisible by 3. Now a plus 4, it is a prime number. So that means this a plus 1, it cannot be a multiple of 9. Now we consider a plus 2, multiple of 9, we can write a plus 2 equals 9k. Now if we add 6 to it, we can write a plus 8 equals 9k plus 6, which is divisible by 3. That means a plus 8 is divisible by 3, which again is not possible since a plus 8 is a prime number. So it cannot be a plus 1, it cannot be a plus 2. If we take a plus 3, then we can write a plus 3 equals 9k, or a equals 9k minus 3. That means this a is divisible by 3, again which is not possible. So again using same logic, we can prove that a plus 5, a plus 6 and a plus 7, it cannot be a multiple of 9. So that means this D, it cannot be 4 also. So there cannot exist 3 prime numbers each greater than 3 which are in AP with a common difference less than 5. That is the first part of the question. Now we'll come to the second part. Now the second part is, let k greater than 3 be an integer. Then we need to show that it is not possible for k prime numbers each greater than k to be in AP with a common difference less than or equal to k plus 1. Let us consider an AP which is a plus d, a plus 2d and a plus k minus 1d, and suppose this is a1, a2, a3 and ak. Now each ai, it is greater than k and its d is less than or equal to k plus 1. Now if for each ai we take modulo d minus 1, then 0, 1, 2 up to d minus 2, it must represent full system of residue for all i's. So there must be at least one number j such that aj congruent 0 modulo d minus 1. That is, aj is some c into d minus 1. Now since all these ai's, they are prime number, that means this aj, it can only be d minus 1. Now d minus 1 is less than or equal to k, but we are given that ai is greater than k. That means there is a contradiction. So it is not possible for k prime numbers each greater than k to be in AP with a common difference less than or equal to k plus 1, and this completes our proof. Now question number 8 is, let in be this integral from 0 to n pi sin x upon 1 plus x dx. Now we have to arrange I1, I2, I3 and I4 in increasing order of magnitude, and we have to justify the answer. Now for this, what we'll do is we'll consider this function fx, which is sin x upon 1 plus x. Now we can draw an approximate graph of this function. So first we'll draw the axis and then we'll draw boundary of this curve, which is y equals 1 upon 1 plus x. So it'll be this curve, and we have studied such questions when we were discussing graphs. I'll provide the link to that video in the description below. Now we'll also need to consider a symmetric curve below x-axis also. Now this is 0, pi, 2 pi, 3 pi and 4 pi. Now we can draw an approximate graph. This is the graph of sin x upon 1 plus x. Now let this area be A, this area be B, this area be C and this area be D. Now clearly A, it is greater than B and L be greater than C and L be greater than D. Now this definite integral I1, it is nothing but it is this value a. Now I2 will be simply a, and then now since this part it lies below x-axis, so this integral will be a minus b. I3 will be a minus b plus c, and I4 will be a minus b plus c minus d. Now since a is greater than b, which is greater than c, which is greater than d, we can say a will be greater than a minus b plus c, and it will be greater than a minus b plus c minus d, and it will be greater than a minus b. That means I1 will be greater than I3, and it will be greater than I4, which is greater than I2. So that's your correct increasing order of magnitude. Now question number 9 is, consider all non-empty subsets of the set 1, 2 up to n. For every such subset, we find the product of reciprocals of each of its element. Denote the sum of all these products as Sn. For example, S3 is 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 1 into 2 plus 1 into 3, 2 into 3, and then 1 into 2 into 3. Now we can write this S3 as 1 plus 1 upon 1, 1 plus 1 upon 2, 1 plus 1 upon 3, and then minus 1. Now this product, it has all these elements. So we can find sum of all these products Sn as 1 plus 1 upon 1 into 1 plus 1 by 2, 1 plus 1 by 3 up to 1 plus 1 by n minus 1. Now we can also write Sn minus 1 as 1 plus 1 upon 1, 1 plus 1 by 2 up to 1 plus 1 by n minus 1 minus n. Now if in this product we consider all these terms up to 1 plus 1 by n minus 1, then it will be equal to Sn minus 1 plus 1. So you can write this Sn as Sn minus 1 plus 1 into 1 plus 1 by n minus 1. Now if we multiply it, we can write 1 plus 1 by n Sn minus 1 plus 1 plus 1 by n minus 1. Now this 1 and 1 will cancel. So from here we can say this Sn will be equal to 1 by n plus 1 plus 1 by n into Sn minus 1, which is what we need to prove in part A. Now part B is hence or otherwise deduce that Sn it is equal to n. Now again if we consider this Sn, it is 1 plus 1 upon 1. Next is 2 plus 1 upon 2, 3 plus 1 upon 3, and it will go all the way up to n plus 1 upon n minus 1. Now this is 1, 2, 2, 3, 3, 4, and it goes all the way up to n plus 1 minus 1. Now this 2 will cancel, 3 will cancel, all these terms they will cancel. We'll get this Sn as n plus 1 minus 1. This 1 and 1 will cancel. So we can write Sn it is equal to n, which is what we need to prove in this second part. Now question number 10 is, show that the triangle whose angles satisfy this equality is a right angled triangle. Now we can write this as summation sine square A will be equal to 2 times summation cos square A. Now what we'll do is we'll also add this summation cos square A both sides. Now the summation here is cyclic summation. Now here will be sine square A plus cos square A plus sine square B plus cos square B plus sine square C plus cos square C. So on the left hand side we'll get this as 3, and here will be 3 times summation cos square A. Now we'll cancel this 3 with 3. So we can write summation cos square A it is equal to 1. Now we'll multiply 2 both sides. So we can write 2 cos square A as 1 plus cos 2A, and it will be equal to 2. Now summation 1 plus cos 2A is 1 plus cos 2A plus 1 plus cos 2b 1 plus cos 2c, it is equal to 2. Now this 2 and 2 will cancel. We can write this as cos 2a plus cos 2b plus 1 plus cos 2c, it is equal to 0. Now we'll use cos c plus cos d. So it will be 2 cos c plus d by 2. So it will be cos a plus b into cos a minus b, and here will be 2 cos square c equals 0. Now cos a plus b is cos pi minus c, which is minus cos c. So if we take 2 cos c common, we can write minus cos a minus b plus cos c, it is equal to 0. Now we can again write this cos c as pi minus a plus b. So it will be minus 2 cos c and then cos a minus b plus cos a plus b will be 0. So from here we get this result as minus 4 cos a into cos b into cos c is 0. That means either a is pi by 2 or b is pi by 2 or c is pi by 2, which completes our proof that it is a right angle triangle.